is what you did in Gen Chem 1, but we're taking it a step further. So your task will be to basically pick up where Gen Chem 1 left off and take it to Gen Chem 2 with regard to solution concentration. Not sure if we'll get through this whole part or not. We'll see. If we do, you can see at the end there's like a boatload of questions. So it's going to be important with regard to intermolecular bonding to be able to talk about solution concentration in kind of a couple other different ways. But in general, solution is a homogeneous mixture. A solution has a lot of S's. I think I complained about this before. You know, it has basically, the thing you have a lot of is your solvent. And yes, you will be using that term coming up. The thing you dissolve in is solute. Now remember, like the solvent and the solute can be liquids, solids, gases. It can basically be anything like that. And if your solvent is water, then it's an aqueous solution. All right. So we talked before, and we're going to talk again about molarity and grams per liter, that sort of thing. Usually when we talk about how concentrated solution is, it's in terms of amount of solute per given amount of solution, which has the solute and the solvent, usually. And we're going to kick in another way of expressing solution concentration that you may or may not have run into before, and it's actually molality. And actually, instead of amount of solution, it's per actually kilogram of solvent. So we're going to kind of throw, there's too many M's. I'm sorry, but there are. So we have these generic terms. A dilute solution means that you don't have very much solute per given amount of solution. Concentrated solution means that you have a lot of solute per given amount of solution. Here we go. So mass fraction and mass percent, and I have examples to kind of remind you how that goes. But anytime you see, of course, mass is weight, so weight fraction, okay? Anytime you see fraction or percent, they actually differ by a factor of 100. So they will be the same number, but they will differ by a factor of 100. We have mole fraction, okay, or relative mole percent. I'm going to remind you, actually, with Dalton's law of partial pressures with regard to gases, we actually had to use mole fraction. We'll be looking at that again. We have volume fraction, which you have a homework problem at the end of this part 8, that uses volume fraction, but it's not one that I use very much. Okay, and then we get to these two. These were definitely Gen Chem 1. Early on, we talked about how do you talk about the concentration of a solution. Well, you can talk about grams of solute per liter of solution, or you can talk about moles of solute per liter of solution. And we're definitely going to continue the factor label method. Okay, so G/L, remember that? That really means grams of solute per 1 liter of solution. Abbreviation for solution is SOL''N. And we spent a lot of time, and because it's really helpful in chemistry to know molarity, which is moles of solute, again, per 1 liter of solution. Okay. Now, the little thing in the box here reminds you that the volume actually is a function of temperature, and so in general, as you take a liquid and it remains a liquid, as you cool it down, the volume gets less. As you warm it up, the volume increases. Okay, so now last but not least, and I'll go ahead and tell you what the ratio is molality. Now right off the bat, don't blame me. Okay, molarity and molality look so similar. They're both the symbol M. Molality is a lowercase m, molarity is an uppercase m. Welcome to chemistry. So molality is a ratio, but like I think I mentioned a minute ago, it's going to be moles of solute. Instead of amount of solution, it's actually going to be kilograms of solvent. Too many S's. Okay, that's what molality means. And because doesn't have to do with volumes here at all, molality is great in chemistry because it does not depend upon temperature at all. Temperature independent. So I'm going to kind of march through those. I don't think necessarily in order. But like I said, some of this stuff is like deja vu, right? Mass fraction of component A in a mixture. We calculate it. This is my calculated set of definitions sort of thing. So we calculate mass fraction of a component by setting aside an amount of mixture. Okay, we take the grams of the component A divided by the grams of the whole mixture of the solution. Okay, we get mass fraction. Mass percent is related to mass fraction by a factor of 100. So if you know, and actually we are going to be piggybacking on we're going to be actually finding the concentration of a solution in different terms. So if you know this one, you just multiply by 100 and you get mass percent. Okay, but if you don't know your mass fraction, I don't know if you guys have this. If you don't know your mass fraction to piggyback on, basically you're going to take a certain amount of mixture or solution, know what the grams are, you're going to isolate the grams of the component, you're going to do a division, and then you're going to multiply by 100%. All right. So we still need to concentrate on units in Gen Chem 2, just like we did in Gen Chem 1. Actually, mass fraction and mass percent can be considered to be unitless to a certain degree because we're taking grams of solute divided by grams of solution or mixture. So grams cancel out and it's unitless. So this is a good reminder, and you're going to want to be able to do this on the previous slide and this slide. You're going to need to be able to unpack those weight percents and unpack those mass fractions to use them intelligibly in your chemistry problems. All right. So the term a dilute solution just means you don't have much solute per given amount of solution. The term parts per million or even more dilute parts per billion are oftentimes reserved for oftentimes environmental samples. Okay, and we haven't talked about those yet, so let me kind of fill you in. Parts per million stands for the part, usually a mass part of A per component A per a million grams or whatever of the mixture. And I think I must have it coming up. Oops. Go back here. Okay. So in other words, and if it's by weight, which it usually is, like I just said, parts per million, if you're trying to calculate it, it will be grams of A, okay, in 1 times 10 to the 6th grams of your mixture or solution. Parts per million. If you have mass fraction, you can piggyback on it by multiplying it by a factor of 10 to the 6th. So parts per million, I have a couple of tricks with parts per million, maybe just one trick. Here's one trick for you. Now this has two conditions. One is that your solvent needs to be water, and it needs to be a relatively dilute solution. If that is the case, then the way the density of water, etc., works out is you can actually use units of parts per million and milligrams per liter of solution interchangeably. Actually, one of your homework is like that. So if it's a dilute aqueous solution, parts per million is the same thing as milligrams of solute per liter of solution, which is basically kilogram of solution because the density of water is one gram per milliliter. So that's how that works out. I've chased it down, but it's true. So that's kind of helpful. All right, so switching gears now to mole fraction. And again, I'm going to kind of remind you where we use this with Dalton's law of partial pressure. But mole fraction is kind of interesting. It kind of feels weird. So you have a mixture, you have your solution, and you have your different components. So basically, to calculate the mole fraction of, for instance, component A, you add all of the moles that are swimming around in your solution together. That number goes in the bottom, and you divide by the moles of the component of interest. Okay, that will give you mole fraction, which is more common than mole percent. Okay, but mole percent, you just multiply this by 100. Okay, so mole fraction is usually X, and then you put a little subscript for what the component is. So mole fraction of A would be that. So this is a slide from Chem 1 when we talked about Dalton's laws of partial pressure. Remember, partial pressure of A can be represented as pressure sub A. And remember, we can get the partial pressure of A by taking its mole fraction times, and I'll go ahead and add a little T here, its mole fraction of that component times the total pressure of the gas mixture. And then up here, seems like so long ago, but up here is how we calculated the mole fraction of A. We came up with the sum of the total number of moles in our gas mixture, put that in the bottom, and then in the numerator, we put the mole fraction, or excuse me, the number of moles of A. All right. Again, mole percent related to mole fraction by a factor of 100. Not used very much. These next two might be very familiar. Okay, so grams of solute per liter of solution, affectionately called G/L. But again, you need to be able to unpack that, okay? If you need to calculate the grams per liter, basically you isolate a volume, then that volume will go in the bottom, and then you need to know the mass of A. Do a little division problem. Speaking of, I was going to chase it down. This problem seems so much like what we did in Chem 1. I guess I was not very creative. But just to remind you how this works. If you need to express the concentration of a sugar solution in terms of grams per liter, and you were given that you dissolved 32.3 grams of solute in a total volume of 225 milliliters. Remember, it's just a quick division problem. You do need to clean it up, though, because units are supposed to be, a volume are supposed to be in liters, and right now they're milliliters. So all we got to do is take the mass, which was 32.3 grams, and in your hints for your homework that looks like will probably be assigned and due Friday, I went ahead and encouraged you, if you see something like C12H22O11 and you don't want to like make your hand cramp, you can basically somewhere denote that that is, you can call that sugar or whatever. You can abbreviate it, but you probably need to go ahead and somewhere say that. And then it's just easier to work the problem, I think. Why make a problem harder than it needs to be? We do it in chemistry all the time, making it harder than it needs to be and simplifying it where we can. So we just go ahead and divide the mass by the volume, but the second term, like I said, is to go ahead and kind of fix the fact that in the denominator we have units of milliliters, and we need units of liters, so we introduce the second term, 1,000 milliliters over 1 liter. We round according to the correct number of significant figures, 3 significant figures, and we get a value of 144. If you, at this point, since there's only one component, want to put 144 G/L, that's fine. Okay. If there were more than one component, that wouldn't work. Okay. So that's how that goes. Actually, we're going to kind of come back to that same 144 grams per liter of sucrose solution in just a minute. So molarity, again, you're like, oh, I know molarity, and I know you know molarity. So molarity anytime gives you capital M, that's moles of solute per liter of solution. Remember, so that is, again, like grams per liter, temperature dependent to a certain extent. So this is just to kind of remind you that if somebody gives you 3.0 big M HCl, that means 3.0 molar HCl. That means there are 3.0 moles of HCl per 1 liter of solution. It's about communication. It's funny because like I told you, my husband teaches this class too, and we both firmly believe that, you know, to get through the course and to be a good scientist, you really need to work on your communication skills. So, and organization sometimes. All right. So, yeah, we're going to go back to that 144 grams per liter, and we're just going to go ahead and knock out, instead of grams per liter, we want it moles per liter. And remember, in Chem 1, we talked about we can use the molar mass to accomplish that. So in Chem 2, you still need to show me calculating your molar masses. So if we take, well, you guys don't have this one. We take 12 times 12.01 for carbon, plus 22 times 1.008 for hydrogen, plus 11 times 16.00 for oxygen. We add them all up, we get the molar mass, the grams per 1 mole of sucrose, which is 342.30 grams of sucrose per mole of sucrose. Remember, since we're adding here, well, we're kind of multiplying and then adding, but the multiplication actually does 12, or the 12, 22, and 11 are exact numbers. They bring no uncertainty. There is uncertainty in those weights gotten off the periodic table. So we're allowed only 2 decimals. So that's how that works. So if we piggyback, and actually in your problems, now when I go to grade your problems on your homework and for solution concentration problems for your homework and for your test, this is where students really kind of come up with some interesting ways to work the problems, which is good, just different than what I do, okay? But, so we're going to piggyback off of this. All we got to do is make grams cancel, be left with moles in the numerator, so we use what, the kind of the flipped version of the molar mass. So 1 mole is sucrose per 342 grams of sucrose. Grams of sucrose cancel. We're left with moles of sucrose per liter of solution. Looks like we need to we're only allowed, what, 3 significant figures for the molarity. And I get 0.419 moles of sucrose per liter of solution, affectionately called 0.419 big M sucrose. Isn't that funny how my spaces are like? I know I used an equation editor before, but like look at that. Like, why is that space there? I do not know. Okay, so that's kind of a repeat stuff. Okay. So molality is a lowercase m, and like I said, molality is a ratio again. It's the moles of solute per kilogram of solvent. Okay? I'll kind of write that again. So moles solute, which they're in a lesser amount, per 1 kilogram of solvent. Solvent doesn't have to be water, though. So molality. And here's another little trick for you. Again, the 2 conditions: if the solvent is water, if it's an aqueous solution, and it's relatively dilute, and I don't have a good cutoff for you what that relatively dilute means. But what you're going to find is that the molarity and the molality of that solution are approximately equal. But don't worry, you're not going to be invoking this, as far as I can tell. But you will the other one. The 1 parts per million is approximately equal to 1 milligram per liter. So like I said before, the cool thing about molality is now it does not depend upon temperature, which I've always been fortunate to do lab experiments that are like at normal temperatures, but yeah. So molarity is generally constant for me too. So I thought this is kind of clever. So we have 2 solutions side by side. This is potassium dichromate. This one on the left is 0.100 molal. This one on the right is 0.100 molar. Okay, so if we start with the molar one, what they did was to weigh out the mass of the solid, which was to get let's see, yeah, these are in, brought it up to 1 liter. So the molar mass must be 194 grams per mole. So they only needed 19.4 grams to get 0.1 moles. They put it down here, they dissolved it probably, brought it up to volume, and like you guys know, volumetric flasks have that one line up there. So that's 1 liter, so that's 1 molar. 0.1 moles of solute dissolved in 1 liter of solution. For this other one, okay, what they did was to go ahead and again weigh out 19.4 grams of potassium dichromate, and in this case they added 1 kilogram of H2O. It's an aqueous solution. Okay, so that's how they made that one. All right. So let's work a problem, shall we? And this is kind of the vein of solution concentrate. This is kind of how these problems go. And let's try, instead of the black marker, let's try green. See if it's any less sticky. Okay. So I think pictures really help. This one doesn't work. That black one. But I didn't really, I kind of want a picture on the board for this time. We'll see. There's my solution, there's my beaker. Now to work these, oftentimes you'll see me kind of just unpack the information that's given, and then I turn my attention to the question. So when it says 70.0% HNO3, I'm going to go ahead and be explicit what that means. It means that there are 70.0 grams of HNO3 in 100 grams, by definition, of solution. SOL apostrophe N. That's what that means. And very rarely, usually you have to use all the numbers that are given. So the density is 1.42 grams per milliliter. Now be careful. When they give you density, unpacking that, that's 1.42 grams of solution per 1 milliliter of solution. You have to be careful with your units. Cool. And then I'll put question mark. What are we after? We are after the 3 things. We are after molarity, and sometimes next to my what we're after, I'll go ahead and say what is molarity? Molarity is moles of HNO3 per 1 liter of solution. That's what we're after. We can do that. We are after molality, lowercase m, and that is going to be, again, moles of HNO3 per 1 kilogram of H2O. It's just HNO3 and H2O. And we're also after mole fraction. So big X of HNO3, what's that going to be? Well, again, I see a pattern here. That's going to be moles of HNO3 divided by moles of HNO3 plus moles of H2O. So, cool. So, and it's, like I said, I think it's interesting when I grade your tests how students do it differently. You can go after these different order, different method. You know, I'm just going to kind of give you some hints. But you see right off the bat, if I know the moles of HNO3, I got the numerator for 3 of those, right? Okay. So I think we've done this before. You need to come up with a basis. And I'm actually going to work the same problem twice. My first basis is going to be the most obvious one to me. In order to pick your basis, you basically look at your constants that were given. You're like, well, what would make sense? So my first basis is going to be actually 100 grams of solution. I'm going to say assume, or basis, assume 100. I'll go ahead and put a decimal, give me 3 sig figs, grams solution. And when we work a few of these, you're going to see why that is. If I go with 100 grams of solution, things start falling into place. Now go ahead and, do you guys have this slide already? We're going to need the molar masses of the HNO3 and the molar mass of H2O to get to our moles. All right. So the reason I chose 100 grams of solution is right away, based upon the weight percent, then I know I must have, like this slide says, I must have 70.0 grams of HNO3. And do you buy this? Since there's only two things added together that make 100%, that means I have 30.0 grams of H2O. That's important. So I'll put this. Assume that, and that means I have 30.0 grams HNO3 and, 70.0 grams of HNO3 and 30.0 grams of H2O, just by definition. All right. So before already you guys can see, and I'm not going to go there yet, but you see where I can take these masses and use the molar masses on the previous slide to get to moles. So dang, I'm almost there, right? Totally. But hold your hat. I want to do one more thing kind of over here. Based upon our 100 grams of solution, because we didn't use density yet, do you guys remember we can use mass of solution, which is 100 grams, we can use density to get to volume. That's exactly what I'm going to do right here. Because I need volume for this one. Okay, so our basis was, I guess it was 4 sig figs, but our basis is 100 grams of solution. Put that over 1, then use our density to get to volume. Of course, we're going to need to what? Flip that, right? Like that. And then we actually want liters of solution, not milliliters of solution. So I think I have one more term on here. No, I don't. Okay, I left it in milliliters. Okay, so as our basis, I'll go ahead and put 70.4 milliliters solution. All right. Well, let's go ahead and do the Gen Chem 1 stuff. Let's go ahead and take these two masses. I'll put these all back up here. These two masses use the molar mass from the previous slide. So for HNO3, we take the mass 70.0 grams times the flipped version of the molar mass, 1 mole over 63.02 grams, rounding it to 3 significant figures, because that's what I got in my mass, 1.11 moles HNO3. And again, if you've kind of done it this way, you're like, oh, you give yourself a star, because that's where these two, you got actually these 3 things. The moles of the solvent, which is water, 30.0 grams, times the flipped version of the molar mass, 1 mole over 18.02 grams, and that gives you 1.66 moles of H2O. That's this one right here. So, you know, if you want to go ahead and start plugging, you could, right? But if we go up to the molarity is moles per liter. So we just need to take the moles, which we've got 1.11 moles, HNO3, divided by the volume in milliliters, 70.4 milliliters. We got to fix the denominator to liters now, don't we? So if we introduce 1,000 milliliters over 1 liter, that should do it. Round it to 3 significant figures, and voila, you have your molarity. Big M. That's it. Okay, can't remember when I go next. Oh, molality, little m. So molality is the moles divided by 1 or per 1 kilogram of H2O. We don't have 1 kilogram of H2O, but we do know what a mass of H2O is. That's exactly what we're going to use right here. There we go. 1.11 moles of HNO3 divided by 30.0 grams of solvent, which is H2O. Well, molality needs to have in terms of kilograms. Now this is the one that always I'm like, is that how that works? But if I want to get from grams of H2O to kilograms of H2O in the denominator, then I'm gonna, introduce a factor of 1,000 grams over 1 kilogram. That's exactly what I'm gonna do. It's all about units. It's all about units, people. So our units look great. We have moles of HNO3 per kilogram of H2O and 3 sig figs, and we're done. 37.0 molality. Now, this just kind of came to me, in physical science problems, like in chemistry problems, sometimes you can look at the answer and you're like, oh, well, that makes sense. Honestly, I can tell you that I can look at, makes reasonable. I look at this, I'm just like, I don't know, it just looks like 37.0 to me. Because I don't have anything, if I thought through it, I might convince myself that's right. But you have to boldly put that number down. So we only have mole fraction left. Mole fraction left. So we put the moles of the solute, 1.11 moles of HNO3, divided by the total number of moles, which is 1.11 plus 1.66 moles. And kind of like mass fraction, we're going to let these moles cancel. And so it's going to be unitless, or it can be unitless. Usually it'll just say 0.104 mole fraction HNO3. And we are going to go with 3 significant figures, even though we have addition and division both going on. But that works. So that's it. So okay, that work? So I'm not going to superimpose it on this, but another way, I'm going to go ahead and walk you through it. It's less obvious to me, but if we would go with 1.00 liters of solution, okay, I'll show you how that works. And I'm kind of thinking that actually we can use this, kind of piggyback on the density and kind of backtrack through it like that. Okay. So if we have 1 liter of solution, we can get to the mass of the solution using the density. 1 liter of solution is our basis. Of course, density is grams of solution per milliliter of solution, so we got to get that to milliliter solution. We can do that by introducing 1,000 milliliters over 1 liter, coming up. And if we introduce the density then, notice that unit-wise we're left with grams of solution. Now I know in Chem 1, so liters of solution cancel, milliliters of solution cancel, we're left with grams of solution. I know in Chem 1, I'm pretty sure in Chem 1, we actually did weight percent and density problems. Weight percent is a ratio of 2 masses, 2 grams. Okay. Density is a ratio of grams of solution per milliliter of solution. So you got to be explicit about those things. All right. So rounding to 3 significant figures, it looks like 1,420 grams of solution. I think the next thing I do here is I can use this ratio with my grams of solution to knock out grams of HNO3. That's exactly what I do. The weight percent unpacked by definition, when it said 70.0 percent by weight HNO3, this is what it meant. Now in this case, our grams of solution cancel. We're left with grams of HNO3, which, remember what we did with grams of HNO3 before, we used the molar mass to get to moles of HNO3, and that's exactly what we're going to do. The math will look a little different, but you will get the same numbers. You should anyway. Rounded to 3 significant figures. The grams of HNO3 in this case, on this basis, are different, of course. It's 994 grams of HNO3. Mass of H2O, we need to recognize that we must have 30.0 grams of H2O per 100 grams of solution. So again, based upon from our volume, we got the mass of our solution, 1,420 grams of solution. We can use the weight percent water to have grams of solution cancel. Be left with grams of H2O. three significant figures, the mass of water you're talking about is 426 grams of H2O. So I think you're already kind of having an idea. We just got to use these masses, apply the molar mass to get to moles. So here we go. Moles of HNO3 in this case, we had 994 grams of HNO3. Use the flipped version of the molar mass of HNO3, 1 mole of HNO3 per 63.02 grams. Grams will cancel, we're left with moles. We need to round according to three significant figures. I got 15.8 moles of HNO3. So we're starting to kind of see some things flesh out over here. Moles of H2O we need for the mole fraction at the bottom. The mass of H2O is 426 grams. Use the flipped version of the molar mass of water, 1 mole of H2O per 18.02 grams. Grams of H2O cancel, we're left with moles of H2O. Round to three significant figures, I got 23.6 moles. 23.6 moles of H2O. So we're ready to do this one. Okay. This top one's pretty easy too, because we got the moles of HNO3, and our basis was 1 liter. So you're like, all right then. All right. We still have to, and we're going to actually, I think we're going to use the density of water, is that right? Okay, so to knock out the molarity, like I said, it's pretty easy, because we had 15.8 moles of HNO3, and our basis was 1 liter of solution. So do the division, I can do that one. So 15.8 big M HNO3. And students, you might be wondering, so I know Mrs. Snipes, you're about labeling and all that, and I'd be cool with just a big M HNO3. Molality. I guess, yeah, we had massive water. Yeah, this isn't too bad. I forgot we had massive water earlier. So we had the moles of HNO3, 15.8 moles of HNO3. The mass of water in grams, 426 grams of H2O. Of course, molality, lowercase m, is moles per kilogram. So we got to fix the denominator. And we can do that by introducing 1,000 grams over 1 kilogram H2O. So now our grams of H2O cancel. We're left with moles of HNO3 per kilogram of H2O, and that's perfect. Round it to three significant figures. It looks like 37.1. Oh, it's a little different. This one was 15.9. I'd accept either one of those. And last but not least is the mole fraction. So we take in the numerator, we have the moles of solute, which is 15.8 moles of HNO3, divided by the total moles, which again is that 15.8 moles, plus the 23.6, which is the moles of H2O. The moles are going to cancel, I think, leave it just unitless. So the mole fraction of HNO3 is 0.401. And that's it. Not too bad. Then we have a whole buttload of problems. Yeah, well, it took me a minute because I didn't have these done, actually more than a minute. So let's take a look at these. Part of the reason I do these is because I think they're fun. Like, some of these are fun, some of these aren't. These like little hints. But part of why I do them is because historically, sometimes I had students like going, I have no idea where to begin. And that always bothered me. So this is actually gives people who want to have it a place to begin. So then I feel less guilty if not everybody hands in their homework, because I at least gave them a place to where to begin. Okay, so the first one, there's my little soapbox thing. So the first one, I'll try not to belabor it too much. It gives you weight percent, NaCl, and then it gives you certain other pieces of information about this particular sodium chloride solution. Notice it gives you what seems kind of random. Oh, wait a minute. Oh, I see a mistake. See that 3 point, this one up here? That should be 3.87 gram. Oh, no, that was right. Oh, no, I did it right. Here, this one. It seems kind of random. They just said that basically gave you density information. They gave you the mass of the solution and what the volume would be. And my hint was, oh, you're after 725 kilograms of NaCl. I would make that your first term. I honestly would, because it says how many liters of solution would you need to do this. And then actually look at the two purple circled things to kind of get you from left to right. It should do the trick. This other one, I think it calls for a vol flask, basically. It said that basically you took some silver sample, you dissolved it up, silver nitrate, excuse me. You got this molar concentration at that volume, and we know what that means by molarity. But the catch was that your silver nitrate that you sampled, you took at the solid, it was not entirely pure. And so you're supposed to see let's see if I gave any other hints. You're supposed to say, how much of this impure silver nitrate would I go ahead and add to that vol flask to make that volume and that molarity? So I kind of broke it into three. This would not, for me, if I was doing it, although you might do it, be one long problem. What I would do, we kind of did this in Chem 1, I would take that volume and that molarity to kind of backtrack to what sort of moles we got swimming around there of silver nitrate. Then I would go ahead and then we're to the purple thing. Once I had the moles, I would use the molar mass to get to mass of silver nitrate that must be in there. And then last but not least, I would say, well, if that's my mass of pure silver nitrate, given this purity, what mass of sample do I need? That's how I would do it. A lot of beakers here. In this case, we were given the molarity of the sulfuric acid and the density, and you're supposed to come up with the mass percent. That might be my only hint. Nope, I guess I didn't. So, oh yeah, the other hint I give you, and again, you wouldn't have to do it, but to me, since molarity is 6 molar, 6.00 moles of H2SO4 per 1 liter of solution, I said use as your basis 1 liter of solution and ultimately get 2 grams of H2SO4 per 100 grams of solution, which is what weight percent is. That's what I would do. This one, now this was an important thing, so I'm glad to tell you some semesters I have not. We'll be dealing more with, I think, maybe we did this before. Anytime you see brackets and something inside the brackets is indicating molarity, capital M. So you're after what is the molarity of sulfate in this water. And it's parts per million, which if you're like me, I don't do a lot with parts per million these days. But remember, if you have a dilute aqueous solution, which this falls into that category, I think the best way to work this is to recognize that you can basically substitute this out as the concentration is 46.1 milligrams of sulfate per liter of solution. Then you have a fighting chance. It's really not too bad then. Because your goal then is molarity and you have milligrams. Your goal is moles per liter and you have milligrams per liter. So you just need to use the molar mass of sulfate. So it's really not too bad. The next one. Again, given weight percent and density, don't forget though, density is 1.57 grams of solution per milliliter of solution. So I just gonna quick give you, in this case, I would use as my basis 100 with 3 sig figs grams of solution. I would. I was gonna look it up. Remember we talked about cis and trans formations, like the cis and the trans. Well, if you are substituting on a benzene ring like this, we go with ortho. Ortho is like opposite sides of the benzene ring, and then, or that's para. Para is that, and then ortho and meta. Anyway, it depends on like which, relatively speaking, of the 6 carbons you substituted. I think that is so cool. I meant to look that up again. So I went ahead and abbreviated para-dichlorobenzene as DCB, dichlorobenzene, just because it seemed like the thing to do for me. So in this case, notice that our solvent is benzene. Hey, it happens. It's not water. Okay, so we are dissolving 2.65 grams of para-dichlorobenzene into this volume of benzene. Notice they give you the density of benzene too. So it kind of gives you some wiggle room with regard to using the volume and the density to get to grams of benzene, which again is your solvent. You're after molality of the paradichlorobenzene. So molality is moles of that substance per kilogram of benzene. So you're almost there, I think. Did I give you any more hints? Okay. Yeah, to me, you can use the volume and the density of benzene to get to grams of benzene. And then, of course, you can get to kilograms from that. And that's going to go in your denominator, or so to speak. And you can use the mass of solute, 2.65 grams, and the molar mass of dichlorobenzene to knock out to moles. So it's really not too bad. All right, in this case, again, another weight percent and density, and you're after molarity and molality. So it's looking like I have a pattern. If you have weight percent, I would go on the basis of 100 grams of your solution. If I have molarity, I would go on the basis of 1 liter of my solution. But I say 1 liter, but it's really 1.00 liters. So go ahead and set up your basis so it's you'll have the right number of sig figs. Okay. Mole fraction of 2 solutions. In one case, and actually I went ahead and abbreviated that CH3, CH2OH, actually that's ethanol. And I learned it way back when as ETOH. So that's my abbreviation. If I'm after mole fraction in that given weight percent, I just unpacked weight percent, means, and it's an aqueous solution, as the problem states, 21.7 grams of ethanol and 100 grams of solution. If you start as your basis 100 grams of solution, you should be able to kind of dissect what is then is the mass of ethanol, what's the mass of water, get the moles of them, and go ahead and kind of come up with the mole fraction of ethanol, kind of like this. The next one, they give us the molality. And what does molality mean? Again, of an aqueous solution, they have to tell you that part. They have to tell you what the solvent is. But unpacking the 0.684 molality, that means the 0.684 moles of urea per 1 kilogram of solvent. And I hear it as my hint. I would use, we hadn't used this as a basis yet, I would use 1 kilogram of water or solvent as my basis and kind of go from there. It's really not too bad either. Okay. Oh my gosh, there's more? Okay. I think is this the last one? Yeah. Okay, good. So in this case, you're supposed to calculate again the mole fraction aqueous solutions given for the first one, molarity and density, and for the second one, weight percent and density. But be careful for the second one. For B, it actually is the density of 2 things, given the density of pure ethanol is that, and let's see, wait a minute. Let's hold that thought. Nope, this one. Final answer. The first density is the density of the solution, SOLN. The next density is the density of the pure ethanol. Okay, and that's it. So, about the time I start feeling guilty about giving you so much homework, I remember